So now we're going round in circles. We've got this component from a toy, some kind of contraption for going round in circles. Maybe it's, I don't know what it is, to be honest. So we've got to try to work this out. Let's have a look. Okay, so we've got these three metal discs which are all joined together, and we've got a spindle in the center. So that's the schematic that we've been given. We've got the radii of the discs, 1.5 centimeters, 3 and 4. I've got forces A and B applied to the 1.5 and the 3 centimeter disc. So A, I'm showing A there applied to the smallest disc, and because the forces are applied along tangents to the discs, it doesn't really matter what tangent I choose. I'm just going for these all to be in a horizontal direction. It wouldn't really make any difference to the problem if they were all vertical but tangential to the discs, or in any other direction, as long as they were in a tangential direction to the disc. So we've got this force A, which is producing a moment of 6 Newton meters clockwise. So it's applying its force at that point. So that's a clockwise moment. B, we're told, is anti-clockwise, so that's why B is there. And then we've got F applied to the largest disc to keep the component in equilibrium. I'm just going to take F. I don't really know whether F should be going in that direction or in this direction, but I'm taking it going from left to right because that's generally speaking the way my brain works. Okay, so what we've got to do is keep everything in equilibrium, and we've got to find out what the magnitude of each of the forces is. So force A produces a moment of 6 Newton meters clockwise. So that means that the magnitude of A multiplied by its distance in meters must equal that moment. And 1.5 centimeters is 0.015 meters. So that tells us that A is 400 newtons. Now what we're looking for is B. B produces a moment of 9 Newton meters anti-clockwise. So therefore B times 0.03 is 9. And that gives us B of 300 newtons. So now we've got to find out what F is. Now we know that the disc is in equilibrium. F is applied to keep the component in equilibrium. So that means that the resultant moment about the spindle in the middle must be equal to 0. So we've got this clockwise moment of 6 plus F times 0.04, because that's 4 centimeters, minus the anti-clockwise moment must be equal to 0. So from that we get F equals 75 newtons. So that justifies my choosing the direction I have for F. If I had got a negative figure for F here, then all that means is my force F would be in the opposite direction, but its magnitude would still be the same.